This video is over oxidation numbers, which is section 8.1 of Hill's Chemistry for Changing Times. So to begin with, this unit presents 4 views of oxidation and reduction, and it gives you 4 definitions. And I know a lot of students see these definitions and they're like, well, if there's so many ways to do it, why are you telling me all the ways? Just tell me one and we'll move on from there. And I totally understand that perspective. But sometimes you have to look at things from a different angle in order to fully understand a problem. So yes, we're going to really focus in on number 4, but the other 3 are also important. It's sort of like when you see these images. We are right outside of Nashville, so I'm a Predators fan. But each of these things has a different connotation for me. So meaning stand with us. That's like from the Stanley Cup, that we are all standing united. It gives you more of that camaraderie feeling. Whereas Smashville, I love that because, you're going to get smashed if you play hockey. And then let's go Preds. I can just picture people chanting that in the stands. And so each of those different logos has a different view that they really invoke within the fans. And each one has a purpose. And so it's the same thing with oxidation. Each of these 4 definitions has a purpose, and the purpose depends on the perspective of the person who's trying to do the science. And so with that, we're going to focus in on number 4 for this video, for this chapter, but there may be a point in your life where it's more important or it's easier to use either of the prior definitions. So in this video, I'm going to briefly explain number 1, 2, and 3, and then we're going to go through number 4 in a lot more detail than what your textbook does. Number 1 is a gain of oxygen atoms. If you have a gain of oxygen atoms, that is oxidation. So if you notice in the first one, you're going from iron to iron oxide. And so notice on the left-hand side, and none of these equations are going to be fully balanced. So I did this for simplicity's sake, just like your textbook does. So just assume they're not balanced, but be okay with it. Okay? All we're saying is on the left side, so the reactants, are there more oxygens or less than your product side? In this case, the reactants gained an oxygen when they turn into iron oxide, and so that is an oxidation. The second one, you've got 3 oxygens on the left, none on the right, so therefore it is going to be reduction because you are losing oxygen going from a reactant to a product. Okay. This last one, this one's a little more tricky because it looks like it's neither oxidation nor reduction because there's 3 oxygens on both sides. So you didn't really gain oxygens, or did you? So look at the left side. You have 3 oxygens for every 1 chromium. On the right side, you have 3 oxygens for every 2 chromiums. So really, you have 1.5 oxygens per chromium. And so you went from 3 to 1.5, and I hope you notice that that is a reduction. The next definition simply says a loss of hydrogen atoms is oxidation. So this is very similar. You looked at the left side, you look at the right side, and you say, did I increase my hydrogens or did I decrease it? In this case, you go from 6 to 8, which means we increased our number of hydrogen atoms. And if you lose hydrogen atoms, it's oxidation. We increased hydrogen, so therefore it is reduction. Alright, definition number 3. A loss of electrons is oxidation. So now we're looking at loss of electrons. Remember, electrons are negative. So if you increase in charge, then you lost electrons because you're losing electrons. You're losing a negative charge. You're becoming more positive. Okay, so when we look at the first one, zinc to zinc 2+. We went from 0 as our charge up to 2.5, or not 2.5, up to 2. And so when we did that, that means we lost 2 electrons because each electron is negative. So if we lost 2 negatives, that gives us a positive 2 charge. Remember those protons that are in the nucleus? We now have 2 more protons than we have electrons. Therefore, that is oxidation. And the next one, you go from 3 to 2. So we went down in charge. So we must have gained 1 electron. Reduction. This next one, we went from a 2 negative to a 0, which means we went up in charge. We went from 2 to 0. So we increased our charge. If we increase our charge, then that means we lost some of those negative little electrons. They were just being too negative for us. We lost them, therefore it must be oxidation. So be familiar with each of these three definitions. Each one plays a different role. Sometimes if you're just looking at from a biochemistry perspective, it's really easy to just to look at oxygen and hydrogen. But from a chemistry perspective, those electrons are really important. But truthfully, in chemistry, number 4 is really more helpful because it lets us assign charges to things that are neutral or things that are within a molecule. So let's go. Let's dig in and figure out what are these oxidation numbers. How can we look at an atom or a atom within a molecule and figure out what its true charge is? That's really all the oxidation number is what is the assigned charge for that single atom within a molecule or by itself. So the first rule is if you increase your oxidation number, boop, so it goes up on this chart, that's oxidation. If you decrease it, bloop, that's reduction. So before we went from -2 to 0, bloop, that's this direction, that's oxidation. So our first rules are if there's only one type of element and there's no charge shown, that means you don't see anything written above here. I don't see a +1, a +2, a -2, any of that. Then the oxidation number has to be 0. So iron, nothing is written, has to be 0. C60, that's a little trickier. There's 60 of them. Sometimes you might be saying, oh, well, maybe there's all kinds of oxidation numbers. No, there's one element. All that's in C60 is carbon. And there's no charge shown. Therefore, each carbon that is inside of this, all 60 of them, each have an oxidation number of 0. Same for the rest of these. So like looking at oxygen, most students want to quickly say oxygen, -2, but that's not true because if you have 2 oxygens and they each have a -2 charge, then that would mean that the whole molecule of O2 has a -4 charge, and it doesn't. It has a 0 charge. So since there's one element type, oxygen, and there's no charge shown, which it doesn't have one shown, then the oxidation number is 0. And that's the way it is for every single atom that is only one type and there's no charge shown. Rule number 2. If there is an element and the charge is shown, then whatever that charge is, that's what its oxidation number is. So notice in each of these first 3, if it showed a 3+, my charge is a 3. My oxidation number is a 3 as well. If copper shows a 2+, that means my oxidation number is a 2. If chlorine shows a negative, that means it's -1. That means its oxidation number is -1. Alright, but then how do these fit in these rules? These are ionic bonds. So remember, a metal plus a nonmetal. Anytime you have an ionic bond, you can just cross those charges in order to create your molecule. Here's your molecule or your compound. And so in this case, your 2 would come up here if you were to uncross the charge, and your understood 1 becomes a -1, which means your magnesium is 2+ and your chlorine is -1. This is all things you've seen before, but of course it's going to come back. Okay? Same thing here. Uncross those charges. Potassium's 2 comes up here to oxygen, making it be 2 negative. The 1 that's understood below the 0 is going to be turning into a +1 up here for potassium. So potassium's 1. So remember, if there's no charge seen, so any superscripts, if you don't see anything, it's understood to be 0. If you don't see a subscript, it's understood to be 1. Alright, so that's the second rule. The third rule says some elements always get their own way. So if you ever have an oxygen and it's combined with any other element, it always gets to be -2. Hydrogen, for our sake, if hydrogen ever combines with another element, it gets to be +1. And fluorine, if it ever combines with another element, it always gets to be -1. So just write these down in your periodic table. Remember that these guys always get to be whatever they want to be, which in this case is -2, +1, -1. Okay, so now let's practice. This rule says if a molecule is neutral, then all the charges must be 0, which makes sense. If we're going to combine hydrogen and carbons together and they combine to have a total net charge of 0, then obviously you can't have all of the atoms being negative or all of the atoms being positive, because then the net charge would be something besides 0. So to begin with, we've got CH4, and we have to remember our prior rules that we've already discussed for this. And so that being hydrogen gets its own way. So hydrogen gets to be +1. And there are 4 hydrogens in this, so it's hydrogens, each of them is a +1. So in order for this to balance out and equal 0, the question is, what does carbon have to be? So if you got 4 positives, in order to balance out those 4 positives, you need 4 negatives. And so carbon ends up being -4. So if I were to ask you what is the oxidation number for carbon within CH4, you would say -4. Let's try it similarly for carbon dioxide. Out of carbon and oxygen, you know oxygen, because remember oxygen had to be -2 from our prior rule. So if that's true, there's 2 oxygens, each one has a -2 charge. That means you totally have a -4 charge. So once again, carbon is going to end up being +4. Now what about water? Hydrogen, we know it's going to be +1. There's 2 of them. Oxygen, we know that it has to be a -2. Does that balance? Absolutely. +1 + 1, -2 gives you a net charge of 0. All right, what about this next one? Does carbon always equal -4? No. So we know hydrogen, it's got to be +1. There's 6 of them, so I did 6 times a +1 gives me a total of 6. So that means I have 2 carbons, and they need to add together in order to equal -6. So if I take 2 times whatever the charge for carbon is, then I need to make it equal -6, because my hydrogens need to balance out my carbons. And if my hydrogens are a +6, my 2 carbons together need to be a -6. So 2 times what number gives me -6? And you should have said 2 times a -3 gives me a -6. So that means each of my carbons has a -3 oxidation number, and each of my hydrogens has a +1 oxidation number. Let's do another one. In this case, we have 2 hydrogens and 1 oxygen, and we know each of their oxidation numbers. So that leaves us with carbon. What is carbon? All right, add those together. +1 + 1. Oxygen is a -2. So if that's the case, -2 + 1 + 1, that gives me 0. So therefore, carbon must also be 0 in order for it all to be balanced out. All right, last one for this slide. We've got HNO2. Hydrogens must be +1, oxygens must be -2. What does nitrogen equal? Well, if you go -2 to -2, that gives me a -4. -4 + 1 gives me a -3. So nitrogen must be balanced out to cancel that. So -3 + 3 gives me 0. So nitrogen is +3. All right, so all of these molecules, notice they're neutral, but each of the individual atoms must balance out to equal the charge, which is 0. If there is a charge on the molecule, like these 3 examples, all the charges must equal the charge on the molecule. So in this example of hydroxide, that's our easiest example, where oxygen we know equals -2, hydrogen equals +1. Therefore, -2 + 1 gives me a -1. Does my -1 equal my charge on my molecule? Absolutely. That's my superscript that you see there. So now what about carbonate? I have 3 oxygens, each one has a -2 charge. Remember, I want to add it all up to the charge, which is -2. So if I have 3 oxygens, each of them being -2, that gives me a total net charge of -6. So what does carbon need to make it be a -2 charge on the molecule? It needs to be +4. Because -6 + 4 leaves me a -2, which is my net charge on the molecule, that superscript that you see on the outside of carbonate. One more example. In this case, we have 7 oxygens. Each oxygen is a -2 charge, so 7 times -2 gives me -14. That means that I want a -2 charge on the whole molecule, so each chromium, Cr2, must equal +12. But my question isn't asking what's the charge or what's the oxidation number for Cr2. It's asking what is it for an individual atom of chromium. And in this case, there are 2 chromiums, so 2 times whatever the number for chromium is must equal +12. So 2 times a +6 gives me a +12. So then does that work out? -14 + 12 gives me a -2 charge on that whole molecule, and therefore the molecule charge does equal the charge. Kind of redundant, but it works. Alright, so from this video you have seen that there are 4 ways through which we can define oxidation reduction. And so each of those ways has a purpose, and the main thing is make sure you know how to do it in any of the 4 ways. But then from this point moving on, we're really going to only use that last part of increasing oxidation number or decreasing oxidation number. So now go read section 8.2 and then come back and ready to watch the next video.